Hello and welcome to this video on projectile motion from ReThink Education. This video runs in parallel to the discussion with the projectile motion cog, so make sure that you sign up there for the maximum benefit that we can actually give you. Now, for this video we're going to run through the problem that you are solving in the discussion, where a boy throws a stone up to a window and times it to determine the time for it to reach the window and then return to his hand. He therefore wants to determine the height of the window and if it will be possible for him to escape out later that night. So before we dive straight into the equations of motion, we need to, as usual, take a look at the force diagram. Once the stone is put in motion, then there is only one force acting on it for the duration of its movement. So what is this force? It clearly must be the force due to gravity. We get the following force diagram for the stone. This force diagram applies for as soon as the stone leaves the hand of the boy to as soon as it arrives back down at the point that it actually started from. Therefore, can you see that it can travel up but it still accelerate down? It can reach the highest point but still accelerate down, and it can come back down towards the starting point but it still accelerates down. I hope you're starting to see the pattern that acceleration due to gravity is a constant in projectile motion problems. It is also worth noting at this point that the stone starts on its journey going up quite fast. It then slows down until it actually stops. This is the highest point that it reaches, and as it's stationary here, the velocity clearly must be zero. It then starts to accelerate back down and finally ends up with a velocity that is equal in magnitude to its initial starting velocity, but it is opposite in direction, as initially it's going up and at the end it's actually coming back down again. Now it's time to look at a little bit more in depth into the projectile motion. We know that it starts with a velocity of v meters per second going up. We don't know the exact value, so we use v as a placeholder. We also know that at the highest point in its motion, it has a velocity of 0 meters per second, as we discussed a little bit earlier. And finally, we know that it returns back down to Earth in exactly the same manner as it left, and therefore the speed at which it's traveling at the same height that it started from must be the same as the initial speed. I include a negative here to indicate that the direction, as we discussed earlier, is now clearly different. It's the opposite. And remember that we're talking about velocities which have to have a displacement and a direction. So for any object in vertical projectile motion, this is going to hold. But one last thing to discuss before we can actually use the equations of motion to tackle the problem is to find out what happens with the time. That's the last variable we need to take care of. So if we specifically look at the one equation in the motion, v final equals v initial plus a delta t, we can analyze the up and down motions separately. If we break them up into these two separate parts, we can see that for the up motion, initially the v up is v up, the final velocity must be 0, and acceleration is g, it's the gravitational constant 9.8 meters per second squared down, and the time to travel this distance is t up. Going down, on the other hand, we get the initial velocity of 0 meters per second, the final velocity is v meters per second down, acceleration is g, and the time to travel this is t down. But we already know that v up is actually equal to negative v down, and therefore you can solve these equations to get the result that time to take due to travel up is exactly equal to the time to travel down. Now this is maybe quite an obvious result, but is an immensely important result when dealing with projectile motion, as it allows you to break up the movement into these two halves, one going up and one going down. You can therefore analyze the stone on its way up, or on its way down, or both, so we choose which one suits us. We therefore know that the total time the stone took to move all the way up and down is 2.8 seconds, and therefore we know that t up equals t down equals 1.4 seconds. We are now in a position to actually solve the question. You know to write out all the variables from the equations of motion, you fill in your known values, and you decide which equation you should use to determine the one or two unknown values. It's a good time to now define up as a positive, which means that everything going up we put a plus in front of, and anything going down we actually put a minus in front of. For example, we know acceleration is always going down, and therefore, because we defined up as a positive, acceleration equals negative 9.8 meters per second squared. It is also worth noting that it really doesn't matter which one you choose, so long as you stick to it for the whole problem. Make sure that you don't mix your directions. We therefore tick off our knowns and unknowns and choose this equation. If we look at the up travel, we only have a final velocity, but if we choose the down travel, we have an initial velocity, which is exactly what we need to solve the equation. We therefore have initial velocity, time, and acceleration as necessary. I'm not actually going to solve delta x for you, as this comes in the discussion, but if you have done it, you should notice that your answer is negative. Is it a problem that your answer is negative? Well, no. Remember that we're analyzing the stone as it falls, and therefore it starts from a positive height and ends up at a lower height. It therefore has actually undergone a negative change in height for our small little picture of what we've taken from the top to the bottom. So actually you have to expect a negative answer to be sure, to be right on. I hope that helps you get to the correct answer. Remember to sign up with ReThink Education if you haven't done so already, and also post all the questions that you might have in the Insights tabs. I'll make sure I keep an eye out there and I'll answer any questions that you have. I'll see you next time. Thanks again for watching. Cheers.